Hey everybody, in this video I'm going to be walking through how to solve a series circuit for voltage, current, and resistance. So if you're a little bit rusty on how to solve any of our values so far in series, this video is for you. So the first thing that I want to look at anytime solving a series circuit is I want to make sure I really know my rules. And I'm going to list those out here for the rules that govern series circuit. These are unique to series only, but can be used on any series circuit. And the first is that our total resistance is equal to the sum of all of our individual resistors. So if I look at my schematic here, if I were to add up R3, R2, and R1 together, I would be able to get the total resistance of the circuit. That makes sense to a lot of students, but definitely something we don't want to take for granted because it's only applicable to series. Rule number 2 is that the current, the electrical current, otherwise known as the amps, is the same anywhere in the circuit. So what that means is, if we were to measure how many electrons were leaving positive and going to R1, that would be the same number of electrons flowing from R1 to R2. That would be the same number of electrons flowing from R3 into negative, or from R2 into R3. No matter where we measure, the amount of current will be the same. And again, that's only for series. Last rule is that the voltage drop at each resistor adds to the total. So what does that mean? Well, we know that we have 14 volts. You can think about that as our electrical pressure. When electrons leave positive and get to R1, we're going to lose some of that pressure because of this resistance. So if I have 14 volts of pressure, I might have only 10 volts of pressure after this resistor. So we'll say at point A and point B, the pressure or voltage here at B will be less than it is at A because the electrons are going to have a hard time getting through that resistor. If that's true, we call that amount of pressure that's changed the voltage drop. Put VD here, voltage drop. That's how much of our 14 volts we lost because of that resistance. And our rule says the amount of voltage lost at R1 plus the amount of voltage lost at R2 and the amount of voltage lost at R3, if we add all those together when we're done, it will equal our total voltage. So those are our three rules. Resistance total is the sum of our resistors. Current is the same everywhere. And the amount of pressure or voltage lost at each resistor adds to the total. I'm going to minimize these rules because we will have to come back to them eventually. Next thing I want to talk about before we solve this is Ohm's law. And Ohm's law is three separate equations that allows us to solve voltage, current, and resistance in a circuit. The first is that the amount of pressure or voltage in a circuit is equal to our current, which I'm going to write with an I. So don't get that confused because it's an I. It still is current or amps times the resistance. that's going to be in ohms. Obviously, this is volts. So our first rule says that the pressure in a circuit, the voltage, is equal to the current, or the amps, times the resistance. That is formula number 1. Formula number 2 says the current, again in amps, is equal to the voltage divided by the resistance. And I'm going to write that in purple just so we have an easy way to differentiate here. So you can calculate how many electrons are flowing if you know the pressure and you know the amount of resistance in the circuit. The third and final version of this equation is we can calculate the resistance if we know the voltage and the current. So those are our 3 equations for Ohm's law. And to solve a circuit like we see here in question, let's see, which question was this? 11 from the homework. We need to use both the rules of a series circuit and Ohm's law in conjunction to get all the values on this table. So how do we do it? Where do we start? By the way, I would have this information in my notes. You can use your notes on tests, quizzes, and finals, and this would be, I think, pretty critical information to have. So, that being said, guys, how do I solve this? Well, if we look at our circuit and we look at this table, as I mentioned earlier, we are not going to worry about power for now, so I'm just going to get rid of that. Okay, so the first thing we look at is what can we solve? What do we know? Okay, if you just start trying to pick random things like, what is the current at R2? Or, what is the voltage drop at R1? Okay, if you start trying to pick those out randomly, you're going to get lost in this problem. You need to look at this problem by asking yourself, what can I solve with the information I have? So what can I solve? Well, right now, I know all 3 resistors. So if I know all 3 resistors in my circuit, I can look at my rule and say, well, the total resistance, or RT, is just R1 plus R2 plus R3. So I can add those up, R1, R2, and R3, to get the total resistance. So if we do in our calculator, I'll write this out. The resistance total is R1 plus R2 plus resistor 3. The resistance total is 780 plus 1.5K, which is 1500 ohms, plus 3.3K, 3300 ohms. I can add those up. This does bring up a good opportunity to say, remember, anytime we're doing math, guys, Ohm's law, rules like this, future equations we haven't seen yet, we need to be in base units without prefixes. If you enter this in your calculator, you should find that RT is equal to 5,580 ohms. So that's how much resistance there is in total. And I can fill that area in on my chart. 5,580. And make sure you use your units symbol. Otherwise, you might make a mistake and forget what you're working with. I like to take my work, minimize it, and move it aside because there's going to be lots of things to solve in this problem. Okay, so if I look at my chart now, I know all of the resistance. So where do I go next? Well, one thing to maybe keep in mind is that if we want to do Ohm's law, if I want to solve for voltage, if I want to solve for resistance, if I want to solve for current, notice that I always need two of the three variables. If I have current and resistance, I can solve for voltage. If I have voltage and resistance, I can solve for current. And if I have voltage and current, I can solve for resistance. If I don't have two of those three, then I can't do Ohm's law. And if we look at where we are in the problem, I have total resistance. I have R1, R2, and R3, but I don't have any voltages. I don't have any currents. So therefore, there's really no way for me to use Ohm's law with where I'm currently at in the problem. When you get to that point, I encourage you then to look back at your rules. As we look at our rules, we see current is the same everywhere. We haven't used rule number 2. I also haven't used the voltage drops add to the total. But you know what? Guess what? We do know the total voltage. It's listed here on our diagram. It just wasn't placed in the chart. So I'm going to go ahead and type in 14 volts total. Okay. Now I can see I have two of the three variables needed to solve for the missing third, which in this case is current. If I look to Ohm's law, I'll see that the current equals I equals V over R. So I'll type, or I'll write, I equals V divided by R, where I have 14 volts divided by 5580 ohms. Total voltage divided by total resistance will give me total current. This gives me an answer of 0.0025. So I'll write that in. And like before, I'm going to circle and minimize and move. Okay, so if I look at my chart now, I know the total voltage. I know the total resistance by adding up each of the individual ones. And I figured out the total current. There is 0.0025 amps flowing anywhere you would measure in this circuit. Kind of like if you had a hose with water moving in it, let's just say that's water moving through your hose. If you checked here in the hose or here or anywhere, you would still measure the same amount of volume of water moving, right? More water isn't moving here as compared to here. It's the same throughout. And the same holds true with electrical current in series. And that's where rule number 2 comes in. Current, 0.0025, is the same anywhere. So therefore, this 0.0025 can be applied to each of these locations. So I'll write those in. It's worth noting that in certain problems, you'll have to solve this in different orders and we'll get to that in the future. But I say that so that you really can know why we're doing each step in the order we are. Hopefully I'm explaining that well. Okay, so we filled out now these 3 spots we didn't know before. And we fill them out because we know that the current everywhere at R1, R2, and R3 must be the same as our total. Okay, so what should we do next? I see that there's a rule about voltage drop. It says the voltage at each resistor adds to the total. So that means whatever answer we get here, here, and here must equal 14. But that doesn't really tell me, the exact number. Is it like 2 volts, 6 volts, and 6 volts, or what are the exact numbers? And anytime we need exact numbers, we should probably look at Ohm's law, where I know voltage equals current times resistance. So if I look at this chart, there's a few ways to look at it. I like to think about it like this. The voltage drop at R1 equals the current at R1 times the resistance at R1. So how much pressure is lost at that 780 ohm resistor is the amount of electrons moving through it times its resistance. So in that case, at VR1, the current is 0.0025 amps. And the resistance is 780 ohms. If I input that into my calculator, I wind up with an answer of about 1.956. volts. I'm going to repeat this same process for my remaining resistors. So for resistor 2, VR2 equals current at R2 times resistance at R2. All right, well, the current at R2 is 0.0025, and the resistance at R2 was 1,500, or 1.5K. If I do that math, 0.0025 times 1,500, I get 3.75 volts. And I'm going to do the last one here, just to be thorough. So for VR3, the voltage drop at R3, we're going to do the current at R3 times the resistance at R3. So if I'm showing on my work, that's 0.0025 times 3,300, or 3.3K. And that ends up being, let's see here, 0.0025 times 3,300, 8.25 volts. I'll shrink this guy down. So this was 8.25 volts. And at this point, outside of the power, we have everything that we need. We should be good. Now, one good way to check your work is to test out rule number 3. Do the voltage drops at each resistor add to the total voltage? So, in other words, does 1.956 plus 3.75 plus 8.25 equal 14? Well, if I throw that into my calculator really quick, 0.956. I get 13.956. So 13.956 is pretty close to 14. The only reason they're not the same or perfect is because I rounded my total current to begin with, and over time, that rounding difference will kind of add up and become a little bit of an issue. But for all intents and purposes, those are the same number. And that is solving this circuit. So how did we do it? We applied our knowledge of series circuits and our 3 rules. We used Ohm's law when we needed, and we were able to navigate this problem. If you have any questions or need further help, please email me and we can set up a Zoom time, or I can record more videos if that is going to be useful. Thanks.